On a clear night, when we look up at the sky, we see thousands of stars twinkling. Most of them are hundreds or thousands of light years away. But one of these stars is remarkably close to us, at least by cosmic standards. This is Proxima Centauri, an inconspicuous red dwarf star in the constellation Centaurus, is our nearest stellar neighbour at a distance of about 4.24 light years. Proxima Centauri was discovered in 1915 by the Scottish astronomer Robert Innes. The star is so faint that it is not visible to the naked eye. Its reddish glow can only be discerned through telescopes. Despite its proximity, it is significantly smaller and cooler than our Sun. What makes it so interesting to science is precisely this proximity. Proxima Centauri belongs to the Alpha Centauri system, the closest star system to the Sun. 4.24 light years. That sounds like a manageable distance. But a light year is the distance light travels in 1 year, about 9.5 trillion kilometers. This means Proxima Centauri is roughly 40 trillion kilometers away from us. To make this number more tangible, if you were to drive a car at 100 kilometers per hour without stopping, it would take you over 45 million years. It is precisely this proximity that has made Proxima Centauri the dream destination of space travel. If it were possible to reach any other star at all, it would surely have to be this one. But as we will see, even this comparatively short distance is an insurmountable obstacle for humanity. To understand why Proxima Centauri remains unreachable despite its relative proximity, we must first grasp just how immense interstellar distances truly are. In our everyday lives, we work with kilometers and miles, units of measurement that function perfectly for terrestrial purposes. In space, however, they quickly lose their significance. Even within our solar system, we speak of millions and billions of kilometers. The distance to other stars completely shatters these dimensions. As mentioned earlier, Proxima Centauri is about 40 trillion kilometers away. This number is so abstract that our brains can barely process it. Let's try a different approach. The fastest man-made probe, the Parker Solar Probe, reaches speeds of over 700,000 kilometers per hour when close to the Sun. An impressive feat, and yet even it would take about 6,300 years to travel to Proxima Centauri. That's longer than the entire documented history of human civilization. Let's look at more realistic mission scenarios. The Voyager 1 probe, which has been traveling since 1977 and has now reached interstellar space, is moving away from the solar system at about 61,000 kilometers per hour. At this speed, it would take more than 73,000 years to reach Proxima Centauri, assuming it were even traveling in the right direction, which it isn't. Even our most ambitious space probes are moving at a snail's pace on a cosmic scale. The fundamental problem is the relationship between speed and distance. To complete an interstellar journey in a human timescale, say, in a few decades instead of millennia, we would have to reach speeds that are a significant fraction of the speed of light. At least 10 to 20% would be needed to reduce the travel time to under a century. But here begins a completely new problem: energy requirements. The energy needed to accelerate a spacecraft to such speeds is astronomical, literally. The heavier the spacecraft and the higher the desired final speed, the more fuel is required. But this propellant itself has mass, which also needs to be accelerated, requiring even more propellant. This problem is known as the rocket equation, and it mercilessly exposes the limitations of conventional propulsion technology. Calculations show that even with the most efficient conceivable chemical or nuclear propulsion systems, the amount of propellant required exceeds any practical limit. To accelerate even a medium-sized spacecraft to 10% of the speed of light, one would need energy equivalent to the annual consumption of entire nations, or more. And that's just for acceleration. deceleration at the destination would require the same amount of energy again. The distance to Proxima Centauri is therefore not just a matter of kilometers, it is a matter of time, energy, and the fundamental laws of physics. What appears on paper to be a nearby neighbour turns out to be a barrier that is simply insurmountable with our current technological capabilities. The sheer distance makes even the nearest star an unattainable goal, at least for the foreseeable future. The distance to Proxima Centauri is therefore not just a matter of kilometers, it is a matter of time, energy, and the fundamental laws of physics. The distance alone might be manageable if we could only travel fast enough, but this is precisely where we encounter the next hurdle. Our propulsion technologies are simply not suitable for interstellar travel. Every propulsion system we have developed so far is based on principles that work within our solar system, but fail on the journey to the stars. Let's start with the conventional rocket engines that have taken us to the Moon and other planets. They operate on the principle of recoil. Fuel is burned, and the resulting gases are expelled at high speed. The problem lies in the rocket equation. To achieve higher speeds, you need exponentially more fuel. For a journey to Proxima Centauri, a spacecraft would have to carry so much fuel that its weight exceeds any practical size. Even a spacecraft the size of a skyscraper would consist of over 99.9% fuel, and still wouldn't be able to reach any significant interstellar speeds. While electric propulsion and ion thrusters are more efficient and are already used in space probes, their thrust is extremely low. An ion-driven probe would take decades to reach cruising speed, and even then, it would be far below what would be necessary for practical interstellar travel. Nuclear propulsion was long considered a promising solution. Concepts like Project Orion proposed powering a spacecraft with nuclear explosions. Theoretically, such a system could reach a few % of the speed of light. In practice, however, it is fraught with countless problems. Extreme stress on the spacecraft, political and ethical concerns, and the fact that even with this approach, travel time would still be centuries. But even if we were to develop a propulsion system that overcomes these hurdles, we would still encounter an absolute limit: the speed of light. Albert Einstein's theory of relativity shows us that nothing with mass can travel faster than light, about 300,000 kilometers per second. This isn't a technical limitation, but a fundamental law of the universe. The closer an object gets to the speed of light, the more energy is required to accelerate it further. As we approach the speed of light, the energy requirement would approach infinity. Even if we could harness all the energy of a star, it would be impossible to propel a spacecraft with people on board to the speed of light. Assuming we could somehow solve all these problems and accelerate a spacecraft to a significant speed, that's when the challenges of long-term travel truly begin. A journey to Proxima Centauri would take several decades, even under the most optimistic scenarios, but probably centuries or more. Over such long periods, life support systems would have to function with absolute reliability. Water, food, and oxygen would have to be recycled in a closed-loop system without any failures. A single critical defect could derail the entire mission. Then there's the radiation exposure. In interstellar space, there's no protective magnetic field like on Earth. Cosmic radiation and high-energy particles would constantly bombard the spacecraft. Over years or decades, this radiation would not only damage the electronics, but also pose a serious threat to the crew's health. The risk of cancer would increase dramatically, and long-term radiation damage would be virtually unavoidable. However, adequate shielding would make the spacecraft so heavy that it would be nearly impossible to accelerate. Communication presents another problem. Even light signals, the fastest form of information transmission we know, would take over 4 years to travel from Proxima Centauri to Earth. A simple radio message and the reply would take over 8 years. Real-time communication with home would therefore be impossible. The crew of such a spacecraft would be on their own, without the possibility of seeking advice or assistance in case of problems. And finally, there's navigation and the risk of collisions. Interstellar space appears empty, but it is riddled with dust, gas, and tiny particles. At speeds of 10 or 20% of the speed of light, even a particle the size of a grain of dust would strike with the force of a hand grenade. A larger object could destroy the entire spacecraft. Evasive maneuvers would be virtually impossible at such speeds, and detecting obstacles at a sufficient distance would pose an enormous technological challenge. All these factors combined paint a sobering picture. It is not just a single hurdle that separates us from the stars, it is a whole chain of seemingly insurmountable obstacles. Each of these problems is extremely difficult to solve on its own. Combined, they create a barrier that cannot be overcome with our current technology and our present understanding of physics. We've all probably seen movies featuring something like generation ships. These could, at least theoretically, make a journey to the stars possible. However, upon closer inspection, the gap between theoretical possibility and practical implementation becomes enormous. The concept of generation ships, huge self-contained habitats that would travel through space for centuries. The idea is that it's not the original crew who reach the destination, but their descendants, perhaps only after several generations. Such ships would have to be small, functioning ecosystems where people are born, live, and die without ever setting foot on a planet. The challenges are staggering. Such a ship would have to be large enough to house a genetically viable population. Scientists estimate at least several hundred to 1,000 people. It would require agriculture, water recycling, an artificial atmosphere, and systems that function flawlessly for centuries. The psychological and social problems are almost unimaginable. How do you maintain the motivation and knowledge for a mission whose destination you yourself will never reach? What happens in conflicts when there's no way to escape or get help? The truth is sobering. Proxima Centauri remains out of reach for us, not just today, but for the foreseeable future. The distance is too great, the speeds we would need to reach too high, and the technological hurdles too immense. We can dream of travelling to the stars, but this dream is unattainable with our current resources. However, this doesn't mean that Proxima Centauri and other nearby stars are scientifically worthless to us. Quite the contrary. With increasingly powerful telescopes, we can explore these stars and their planets from afar. We can analyse their atmospheres, search for biosignatures, and learn more about conditions on other worlds. The James Webb Space Telescope and future generations of observatories will give us insights that were unimaginable just a few decades ago. We don't have to physically travel to the stars to understand them. Perhaps there's a certain humility in that. The universe is unimaginably vast, and even our nearest stellar neighbour lies beyond our reach. It reminds us how small we are and how limited our capabilities are on a cosmic scale. Proxima Centauri will continue to fascinate, inspire, and challenge us, but we won't be able to reach it anytime soon. I hope you enjoyed the video. I would be very grateful for your support, and I look forward to seeing you next time.